2, baby.
I heard you can't split class there. We'll go over on our projects.
Hello and welcome back to Calculus2. So we talked about the power series and we talked about properties of power series where we discussed the convergence of power series. And we looked at those three examples and we saw that power series can converge everywhere, which means for every x you think of, could converge for an interval for the power series between two numbers, and can converge at a single point. So now I'm going to theorem. So we're going to take a look at the convergence of power series. So as a theorem.
This class got me.
Convergence of power series.
It's 9.3.
No. So we can have number one converges for all x, which means negative infinity to infinity with radius being infinite. Number two converges on interval x is between two values a and b, and the radius of convergence in that case would be given by b minus a over 2. 3 converges at a point x equals, say, a, with the radius of convergence 0. Obviously, if the power series diverges for all values of x, we don't care about it, right? It's not useful to us for most part. So the power series either converges on one of these three or otherwise diverges everywhere else. Now, I mentioned earlier that the power series are extremely important because power series give us approximation to any function you think of, right? So we've seen approximation for ln, we've seen approximation for sine. Maybe you've done, as I asked you to practice approximation for e to the x. So if you've seen that, you know that every single one of these functions is turned into a polynomial, and polynomials are easy to differentiate, integrate, and so on. Now, as it goes with every upgrade, when you go from numbers into variables, you get those algebraic expressions, and then you can add and subtract and multiply algebraic expressions and so on. Now, when you upgrade from series into power series, you can combine power series. Now, this is a very important part, especially the composition of power series, because your 9.4 depends on that skill. But moreover, all of this stuff is going to be very important for your differential equations course. I did say that 100% of your Calculus 2 course is the prerequisite for differential equations. So if you don't do well in this class, DFQ will definitely be a disaster. So make sure you learn these concepts for the sake of the future, not just the test that it's next time. Combining power series. So this is very important now. Sum and difference. So what we can do is we can put two series together as long as they start with the same counter number and they have the same exponent on x. So if those two conditions are met, the two power series can be combined into one under addition or subtraction. So if you say that power series, so suppose summation ck x to the k converges to f of x, and summation of dk x to the k converges to g of x on interval I, whether that interval I is infinite or finite or a point. So it converges, right? Number one, addition or subtraction of two power series can be brought into a single power series which is simply f plus g. And there is a minus as well. So whether you're adding or subtracting. Now what's important is that when you have over here k equals some number, let's say n, going to infinity, then you have to set same k equals n and k equals n. So the counter has to match and the exponent has to match, and then you are able to absorb, right, put the two into a same one. Number two, multiplication of power series by another x to the m. So if you have x to the m in front of power series ck x to the k, you can bring in x to the m in front because summation operates on k's, not on m's. So you can have k plus m in the exponent. And number three, so number one and two, this is what you are pocketing for your differential equations. Number three, you are pocketing for 9.4. So that's today. And then obviously next week. So function composition. Function composition says if h of x is equal to bx to some m, then summation ck of h of x to the k converges to a composite function. F of h of x for all x in interval I. Now that one doesn't say much when you look at it this way, in this form, but I'm going to do examples now, and that will clear up. So example for number one. If I have summation n x to the non-coughing n going from 1 to infinity, and I need to, let's say, add that to summation of I don't know, n squared x to the n, but this one starts from 2 to infinity. Well, you can't simply combine these because they're not starting their counter at the same number. So what you're going to do is you are going to peel one term over here, and that will shift it so they start at the same point. So when I peel the first term for number 1, I'm getting x plus summation, now it's 2 to infinity n x to the n plus summation 2 to infinity n squared x to the n. So what I did is I peeled the first term. I peeled the term n equals to 1. That's the term that I peeled. So when I plug in n equals to 1, I get 1 times x to the 1. Well, that's just x. And then plus the rest of the series. So now my series will start at 2 because I peeled off one term. Just like factorials when you peel off the last number, right? And then you're left with previous numbers. Over here, you peel the first one and you're left with all the others, right, that come afterwards. So now when you do that peel, right, you over here you have your x plus, and now you have the big sum, right, 2 to infinity, and you will be factoring x to the n, so you get your n plus n squared times x to the n. So we are able to combine these two into this one plus the term x. This stuff, you'll be sick of this in chapter 3 for differential equations. Example for number 2. Another thing that you will have in differential equations when you deal with the power series for Euler equation is when you have x squared summation, let's say n x to the n, with you start, let's say, at 0 and go to infinity. Doesn't matter. For these particular problems, you will be importing x squared inside, so you will have summation 0 to infinity n x to the n plus 2. And then you would go from there. So x squared can be imported in, and then x to the n times x squared is n plus 2, right, in the exponent. So that's example for 2. And now, finally, example for 3. Now, this is a big one. This is the one that you are going to use on your exam on Tuesday and possibly Thursday. So what you have here is a composition of functions. If you remember, I'm going to erase this. I just want you to remember this. From pre-calculus 1, composition of functions. You have f given as, let's say, sine x, and you have g given as square root of x. You compose f with g, so f composed with g was f is the main function, g gets plugged in, so that will be sine square root of x. Or you can compose g with f, that will be square root of sine x. So whatever is your main function, its x will be replaced by the function that it's imported. So you see the main function is f, so the whole thing looks like sine x. On the bottom part, main function is g, so the whole thing looks like a square root function, right? So this is what we have from pre-calculus 1 when you do function composition, which you guys used obviously for your chain rule in Calc 1, and then eventually inverse chain rule for U sub. So now we'll do this with series. I want to represent series e to the x squared. Now, why would I want to represent this series, this function as series, right? What is this equal to as series? Power series. So what is the power series for e to the x squared? Well, those of you who did work at home, you know that e to the x is given as 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... going forever. So you know this. Now what I'm going to do is I'm going to use a function composition. So function composition will replace x with x squared. So on the left hand side, I have e to the x squared. On the right hand side, I have 1 plus and now I have, instead of x, I have x squared, plus, now I have the fraction, which will be something squared over 2 factorial, plus something cubed over 3 factorial, plus something to the 4th over 4 factorial, plus going forever. All of these somethings are x squares. So you can have, if you had e to the blah goes for every single x squared in that exponent. So that is the function composition. And now, when you work out algebra and everything, e to the x squared is equal to 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6 plus x to the 8 over 24 plus ... going forever. Now, why do we do this? We do this because we can't integrate e to the x squared. So what is 9.4? 9.4 is going to use this skill because in 9.4 I'm going to ask you, what's the integral of x squared? Now you covered 6 different methods for integration and none of them can solve it. Right? If you have x e to the x squared, yeah, you sub, not a problem, right? But if you just have x squared, none of the methods you learned work. So what do? Well, you now have the power, right, to turn any function into a polynomial. And how hard is to integrate a polynomial? That's a joke, right? We've seen last class that these approximations, the polynomial approximations, are very, very, precise, right? They're very good approximations. So you keep 4 or 5 terms, it's really good. Well, there is a clear benefit in having 5 polynomial terms which you can integrate like this versus having a 1 term that you can't do anything with, right, which is e to the x squared. So clearly this has a lot of power within. So that's the properties of these. Now, further properties are calculus properties where you get to differentiate and integrate these things. And this is why I don't understand why they split this stuff, right? Because the next theorem is showing you that if you want to do calculus of power series, right, you will differentiate the power series and integrate the power series, which is done term-wise. And then they have a lecture on the 9.4, which is called Calculus of Power Series, which is, you do this. Why? I don't understand it, but I don't need to understand. I just need to get through it. So I'm not going to give you these definitions and things because I have to save it for 9.4, where we are actually going to do the calculus for these things. So that's it, guys. We had a chapter 8. Chapter 8 had 2 concepts in it. Sequence, which is just ordered list of numbers, and series, which is sum of the sequence. So both sequences and series either converge or diverge. They converge to a finite value, meaning that all of the numbers tend to a certain limit, or the series adds to a finite value. If they diverge, for sequences it means it goes away from any value, and for series it means it adds to one of the infinities. We covered 10 tests for series, and you have the sheet that I gave you, which contains all tests in that chart. And we covered only 1 test for sequence, and that is the limit test. So you just take the limit of a sequence, and if it ends up being a finite number, it's convergent, and if it doesn't, it's not. So technically you have 11 tests, 1 for sequence and 10 for series. Then we moved to power series. We introduced x. So in that x, when we introduce x within a series, it becomes a power series. We have x to the k in the power series. And we learned that the power series are actually polynomials. And the polynomials will will approximate any function you put out there to transform it, as you can see over here. So when we have power series, we have to worry about interval of convergence and radius of convergence, because we want to make sure that the formula we have for series, for power series, converges to a function that we are examining. So that's that. And finally, we have the properties where we can add, multiply, and then do the function composition for these. And I told you that the function composition is the one that you really need to know well for your next exam. But then the first two properties, adding and multiplying, will be heavily used in differential equations. So now the next lecture, 9.3, is on Taylor polynomials, which is actually what we already know and discussed from the previous thing. So let's restart this.